Hello and welcome to this project on Intel image classification. So in this project, we will be working on Intel images, that is images of different streets, buildings, forest, etc. as you can see here, and we will build a convolutional neural network, that is a CNN, and we will train it on these images. It is a multi-class classification problem, and to solve this problem, to make this project, we will use Keras. So the steps to solve this problem, to make this project, involves: first, I'll show you how you can mount your Google Drive on your Colab notebook. After that, we will visualize some of the images that we will be working on. Next, we will analyze the dimensions of all the images and verify if they have same dimensions. Next is the important step where we will convert these images into a NumPy array and we will normalize these images. After that, we will check for class imbalance. We will check how many images are there per class. Next, we will split this data and perform the one-hot encoding on the target data. After that, we will create the model architecture in which we will define different layers that will be used, like conv2D or max pooling 2D and all that. Then we will compile the model using the loss optimizer and metrics, and finally we will fit the model. After fitting, we will plot the accuracy and the loss against each epoch, which will show us how our model is learning. After that, we will pre-process the test data and make the predictions on it. And in the end, we will visualize the original and the predicted labels for the test images. So this project can be used for educational purposes and to get a better understanding of how to create a neural network architecture, a convolutional neural network. You can further hyperparameter tune this model or any CNN model to reach a higher accuracy. This project has a vast scope. It can be used to classify satellite images, drone images, Google images, and every other sort of images into different classes like sea, mountain, buildings, etc. So let's get started. For this project, we will be using Google Colab, as Google Colab provides high computational power and CNN requires that. So as we know that in this project, we will be working on Intel images, that is images of buildings, forests, streets, etc. And we will build a convolutional neural network and train it on these images. It is a multi-class classification problem and we will use Keras for this. So let's get started. So first I'll show you how you can mount your Google Drive on your Google Colab, so you can use the dataset directly from your drive. And for this, you first need to upload the data on your Google Drive. We'll run this command, which is from google.colab. We will import drive and we'll drive.mount. Let's run this. So this will prompt you to give an authorization code to this. And to generate this authorization code, you need to go to this URL. You can click on this, select your Google account, and you can allow this. After you allow this, this is the code. You need to copy this code, paste this code here, and run it. So this will authorize the drive with this Google Colab. Here you can see that we have mounted our drive here. So after executing it, now we'll see what are the images or what are the files, what are the folders that I have on my drive. For this, we will run this cell. So here you can see that I have these different folders on my drive and we'll use this Intel image dataset. This dataset contains images that we will work on. After this, we'll import some required libraries. This is one of the most important step. So here you can see that I have imported all the layers that are there in that we will be using for CNN, for building our CNN model. You can see here that we are importing conf 2D, we are importing max pooling 2D, activation, flatten, dropout, dense, and leaky redo also, which is an activation function but implemented as a layer. Here you can see that we will also use batch normalization. We are creating a sequential model, so we also need to import sequential. We have imported optimizer as Adam. Other than that, we are also using NumPy for mathematical computation, pandas for data frame operations, and similarly other libraries for visualization and image processing functions. So let's run this cell and import these required libraries. So after importing the libraries, we will check the folder in the class images, what all folders or what all classes we will be working on in our dataset. So let's run this. So here you can see that the folders it contains is buildings, forest, glaciers, mountain, sea, and street. So these are around 6 classes that we will be working on. Let's plot one of the dataset. Let's visualize some of the images. So here I am visualizing the mountain images. So you can see that we will plot this 25 images in a 5 by 5 subplots. We are using the plt.subplot, that is a function of matplotlib.pyplot. So here you can see all the images of the mountains, and you can see that these images are in 150 by 150. Now let's move forward. Now we will set the root directory for our dataset, and we will store all the folders name of the dataset. We are also creating 2 empty lists for images and label. Let's run this cell. So this will create 2 empty lists. Now what we'll do, we'll read all the images and convert them into a NumPy array. And also we are resizing the images. If there are some images that don't have the similar dimension to 150 by 150, then we will convert all those images into 150 by 150. Let's run this cell. It will take some time because it depends on the type of images you are using or the number of images you are using. It will take some time because it has to convert each and every image one by one into a NumPy array. Also here you can see that in the end we are also appending the image list with the image. It will take around 5 to 10 minutes. So it took around 30 to 45 minutes to run this cell. So next we will visualize the images per class. So for that, and we will store that into label underscore counts variable. So here you can see that we have 553 in glacier, 525 in mountain, and so on. Next we will store the number of the classes which will be used further in the model architecture. So here you can see that we are working with 6 classes. So here we are checking the shape of the input layer. It will be used in the model architecture. So we have 3000 images which are of the shape of 150 by 150 by 3. 3 is the channel, which is RGB here, as it is a colored image. After this, here you can see that we are checking the number of labels in Y data, and it should be equal to the total number of images. Here you can see that it is 3000, exactly same with the total number of images. Now we will train test split our data Here you can see that we are using train test split from sklearn and passing the data. Other than that, we have passed the test size equal to 0.2, which will split the data into 80:20 ratio. That is 80% training and 20% testing. Let's run this cell. So after splitting our data, this is the most important step. Here we are normalizing the data by dividing it by 255, and we are also reshaping the data in the X-train and X-test. Let's run this cell and normalize our data. It will take some time because we have around 3000 images. It's done. This is also an important step. Here we are using label binarizer and we are one hot encoding our Y data. And we will also print the sequence of the classes here. So here you can see these are our classes: buildings, forest, glacier, mountain, sea and street. After this, we need to split our data, our training data into validation and training data. So we are doing that here. Let's run this cell and split our data into validation and training. After this, this is the most crucial step. Here we are defining the architecture of the model. So here you can see that as we are creating a sequential model, so we have put model equal to sequential, and we are passing all the layers as a list to this. So the different types of layers we are using are the conv2d. Here you can see that we are using conv2d with a kernel size 3x3 and filter 16. Here you are see that we have passed the input shape, that is 150 by 150 by 3. After that, we are using a batch normalization layer, a leaky ReLU activation, and similarly other conv2d. You can create your own architecture. You can create different types of layer that you want. It is a hyperparameter and you can tune it according to you. After that, we are using a flatten layer. When the conv layers are done, we are using a flatten layer to flatten it, and we are applying a dense layer. In the last layer, you can see that as we are it is a multi-class classification problem and we have 6 classes, so we are using the 6 neurons in the last layer, and the activation function is softmax. And in the end, we are printing the model summary. So different layers that we have used here are batch normalization, which is a technique for training very deep neural network, as it standardizes the input to a layer for each mini batch. Leaky ReLU, it modifies the function to allow small negative values when the input is less than 0. We have used conv2d layer. It is used to create convolutional kernel that is convolved with the input layer. Similarly, max pooling, which is used to downsample. That is, it takes the maximum value over the window. And a flatten layer, which flattens the input and creates a 1D output. After that, we have used dense layers. So let's run this cell and print out the summary of our model. So here you can see the summary of our model, all the layers that we have provided and all the parameters. In the end, you will see that there are around 306,422 total params, out of which 305,718 are trainable and 704 are non-trainable. So let's move forward and compile it. So for compiling, we need to pass 3 parameters, namely loss, optimizer and metric. Here you can see that we will pass loss as categorical cross entropy, optimizer as Adam with our learning rate of 0.0005 and metrics as accuracy. Let's run this cell. It has compiled our model. After that, this is the important step. This is the fitting of the model. So for fitting of the model, we are using around 70 epochs and a batch size of 128. You can try for more number of epochs to increase the accuracy. So during each epoch, we can see how the model is performing by viewing the training and validation accuracy. And for fitting, we are also passing the validation data here and storing this fit into a history variable. Let's run this. So it will take some time because we are running it for 70 epochs. Let's see how much an epoch takes, and according to that we can calculate how much time this total 70 epochs will take. So here you can see that first step took around 137 millisecond. It's running right now. While training, you can also see the model performance here, the loss at every epoch, the accuracy and the validation loss and validation accuracy at each epoch. So it is completed, and it took around 3 to 4 minutes for this. So now next we will save this model. So we need to save this model for use it later stage for prediction. So we will save this model, and I have passed the path as my drive. So it will save on my Google Drive. So here we are saving the model. After saving the model, let us visualize the training history. Let us plot the accuracy of the model for the training history. And for that, we are calling the history accuracy and history validation accuracy and plot it against each epoch. So let's run this and visualize the training history. So here you can see the training accuracy as the red line and the validation accuracy as the blue line. The model is showing some overfitting, and in order to reduce overfitting, we can use different techniques, like we can use regularization, we can use dropouts, and you can optimize the model. Similarly, we will visualize the loss. For that, we are using the history loss and the history validation loss and plot it against each epoch. So this is the graph for the loss the model is showing. Next, we will see accuracy on the test data. So here we are evaluating the model on the test data and finding out the accuracy. So the accuracy of the model is around 76.66%. You can optimize this model, you can hyperparameterize this model and generate a higher accuracy. Now we'll generate some predictions for the test data and store them into Vipred. So all the predictions for the X test will be stored in Vipred. Now we will visualize an image, and it will be used in further steps to be predicted. So this is the image that we will be predicting. As you can see, it looks like a C. Here we will create a list of label using object of label binaryzer, and we are also printing out the prediction and the original label of the image we visualized above using the argmax function. Let's run this cell. Here you can see that these are our classes, and it originally was, this image was C, and it also predicted as C. So our model is working absolutely fine. So with this, we came to an end of this project. In this project, we saw how we can create a CNN using different layers. We normalize the data, which is an important step with any type of dataset we use, and we will use this model to predict the class of the image supplied to the model. The scope of this project is very vast. It can be used to classify satellite images, drone images, or Google images into different classes like sea, mountains, etc. Next, I will show you how you can create a Flask app for this project. How you can create a Flask app of Intel image classification. So here you can see that I am using Atom as my code editor. We need to create some Python scripts and some HTML files for creating a Flask app. I've created a folder named Intel Image Classification App, and these are all the required files in it. Let me guide you through each file one by one. So first, let us see what is the config.py file. So .py format is format for Python script. So let's see what is in config.py. So in config.py, you can see that we have defined a class config with an object, and we are passing a secret key, that is PyAnalytics. You can change it to anything that you want. Other than that, we have taken session cookie secure as true and default theme as none. Similarly, we have also created a class for development config, and in this we have set debug equal to true. So this is the configuration file. After that, let us see the app.py file. So this is the app.py file. In app.py file, you can see that we have defined the main of a function, and whenever the main is called, app will run. So this is to run the app. Next, let me show you the init py file. So this is the init.py file. Here what we are doing, we are importing Flask from Flask. After that, we are passing the name of the app in the app variable, and then we are calling the config. So here you can see that we are calling the development config, as we have already defined it in config.py. And after that, in the fourth step, we are importing views from app. So let's see what is views.py. So this is the views.py file. So views.py file is exactly similar to the code that we have written in Google Colab. It is just we need to write it again in a Python script so that we can call it. So here we'll see what are the important libraries, important imports we are using here. So here you can see that from Flask we are importing request, render template and URL for. We are using models from Keras because we need to load the model that we saved in our Google Colab. We will call that model here for prediction. We are using NumPy for mathematical computation. We are using image function from PIL, which is used for opening the images, and similarly some other libraries also. After that, we will add the path to config. So here you can see that app.config initial file upload. It will set the path to app static uploads. Next step is to load the model that we have already saved. So this is my path of the model, app static model intel image.h5. This is the model, and I'm saving it in a variable named model. Now we will route to home page using two methods. This is the route. Here you can see these are the two methods, get and post. So initially get method will be executed and it will load our index.html, that is our main page. And as soon as we click on any button or do anything on our home page, the post will be activated. So in the post, you can see that first we are generating a unique image name. After generating the unique image name, we are reading, resizing, saving and pre-processing the image for the prediction using different functions from OpenCV and NumPy. After that, we will predict the output using the model.predict and argmax function, as we know. And these are the classes here defined. We know that we were working on 6 classes, so these are the name of that classes. And in the end, we will return our prediction. In the end, you can see that this is the main function and it will run the app, which is app.run, and here debug is set equal to true. So now let me show you how to design the front end of this application, how this application will look. So for that, we have designed an index.html file. So here you can see that this file is designed using HTML and CSS. So in order to get an understanding of this file, to get an understanding of HTML and CSS, you should previously have some knowledge about it. So here you can see that in the first division, we have set Intel image classification app as our heading and made by PyAnalytics. Next, in the next section, in the next division, we have created a button named upload image. So in upload image section, we have created a button named browse. So you can browse, click on this browse button and browse through the system to upload an image. In the next section, we have created a prediction function, predict function. We'll click on that, submit that, and it will give us the prediction along with the image that we have uploaded. In the end, you can see that these are some of the scripts. So what these scripts does, these link our buttons or our prediction function to the function that is required on that click, and it will save those values. So this is the index.html file. So as I have told you that we have worked on HTML and CSS. So let me show you where they are stored. So in the static folder, you can see that this is the CSS folder, which contains the materialize.css, because we have used materialize.css. We've taken the images like the white background image for the application used in the first division. We have also worked on JS, that is materialize.js, which is saved here. And the model is also saved here with the name intelimage.h5 and the upload files. Now let me show you some of the important files that are required. So this is the proc file. So proc file is generally required for application deployment. Here you can see that we are using web in the starting, because it will tell us the deployment protocol to consider this as a web application. And that after that you can see that Gunicon is in command, and Gunicon will tell the system that we have to call app from app. Other than that, this is the readme file. It contains all the information on how to run this project. And the most important file is the requirements.txt. So requirements.txt, it contains all the dependencies, all the libraries that are used in creating this app with their version. So we can create this requirement.txt file. Let me show you how you can do that. So for that, we need to copy the path of this particular folder where our project is saved and open Anaconda command prompt and move to that particular folder. So let's see how we will do that. So in the Anaconda command prompt, we first need to move to that folder where our project is saved. I have already copied the path for that. Now I'll type the command cd, which is change directory, and paste that path here and move to that folder. So in order to create a requirements.txt file, we first need to install pip reqs on our system. So for that, we need to run the command pip install pip reqs. So here you can see that it is showing me that requirement already satisfied, because I have already installed that on my system. And after installing it, you need to run the command pip reqs. So what this command will does, it will render through every Python script you have written. It will note all the libraries that you have used and note them down into a requirements.txt file with their version that we have used. So here it is showing me a warning because I have already made a file, but it will not show an error on, it will not show a warning on your system if you are creating it for the first time. So in order to run this app, we should have all these requirements satisfied on our system, all these requirements installed on our system. And how we do that? For that, we will use the command pip install -r requirements.txt. So what it will do, it will check all the requirements that are there in my requirement file and it will install those. So here you can see that all the requirements on my system are already satisfied. So it is showing me requirement already satisfied. So we are good to go and we can run this app. So how to run a Flask app? First, make sure that you are in that particular folder where your application is saved, where your project is saved, and you should know the name of your application. The name of our application is app.py. So to run that, we will type the command python app.py. So here you will see that it will provide us with a URL where our application will run, and we will go to that URL. Here in the end, you can see that this is the URL, localhost. Let's copy this and go to our browser to check if our app is running fine or not. So I have copied the URL, pasted it in the URL bar. So this is the application you can see here. It is Intel Image Classification app made by Pi Analytics. This is the front end of our app. So if you know HTML and CSS, you can design this more visually appealing according to you. So now let's check if our application is working fine or not. So for that, we will browse to an image. So I've opened an image here, and let us click on predict and to see if it is working or not. So here you can see that this is an image of a street and our model has predicted it as street. So our application is working absolutely fine, absolutely correct. So with this, we came to an end of this project, this application. Thank you.